Uh, Good day, everyone. I am Jamaru Sabanal, and I am going to discuss the chapter 6, which is the capacitor and inductors. So first, we're going to talk about capacitor. A capacitor is a passive element designed to store energy in its electric field. A capacitor consists of two conducting plates separated by an insulator or dielectric. So, how does a capacitor work? Unlike the battery, a capacitor is a component that temporarily stores electrical energy through distributing charges particles on generally two plates to create a potential difference. A capacitor can take a shorter time than a battery to charge up, and it can release all the energy very quickly. The capacitor is said to store electrical charge. The amount of charge stored, represented by Q, is directly proportional to the applied voltage, so that Q is equal to capacitance times voltage. So later on, ato ra ni magamit this formula sa ato ang problem solving. So let's proceed to the next slide. Capacitance is the ratio of the charge on one plate of a capacitor to the voltage difference between the two plates measured in farads. We should note that the 1 farad, 1 coulomb per volt. Although the capacitance C of a capacitor is the ratio of the charge per plate to the applied voltage, it does not depend on Q or depends on the physical dimension, this one. So where A is the surface area of each plate, while the D is the distance between the plates, and it's the permittivity of the dielectric materials between the plates. In general, there are three factors to determine the value of the capacitance. First is the surface area of the plates, where the larger the area, the greater the capacitance. The spacing between the plates. The smaller the spacing, the greater the capacitance. The third will be the permittivity of the material. The higher the permittivity, the greater the capacitance. Typically, capacitors have values in the picofarad to microfarad range. We should note that according to the passive sign convention, if V is greater than 0 and I is greater than 0, or if V is less than 0 and if I is less than 0, the capacitor is being charged. And if V times I is less than 0, the capacitor is discharging. And it is very understandable naman nga, klaro kayo ang pagka-explain here nga, if ang V o ang I is greater than 0 or V o ang I is less than 0, ang capacitor is charging. And while if ang V og times I less than siya sa 0, so the capacitor is discharging. Current voltage relationship of the capacitor, we take the derivative of both sides of I is equal to dq over dt. By differentiating both sides, we could get the formula of I is equal to C dV over dt. Later on, makita rin na, madiscuss rin nato sa ato ang problem solving. So let's proceed. So capacitor that satisfy equation 6.4 are said to be linear, which is this one equation. And for a nonlinear capacitor, the plot of the current voltage relationship is not a straight line. Next is the voltage current relationship of the capacitor can be obtained by integrated both sides of equation 6.4. We get these formulas. We could get these formulas, and we could later on we could use this formula on our problem solving, where VTO and QT sub O I0 divided by C is the voltage across the capacitor at the time of T sub 0. So, and the equation to this one, Vt is equal to 1 over C, integral of T, To, T0, I, tau, and then d tau plus Vt 0. They show that the capacitor voltage depends on the past history. Hence, the capacitor has a memory property that is often exploited. And this one is, yeah, the instantaneous power delivered to the capacitor is P is equal to VI is equal to CV dV over dt. And the energy stored in the capacitor is therefore, we could just use this, the value is equal to 1/2 CV squared, or we may rewrite it to W is equal to Q squared over 2C. To this formula, we could, what do you call this? Dire na to makuha ang energy stored by using this formula. So, yeah, as what I had said earlier, nga katong nga equation is represent the energy stored in the electric field that exists between the plates of the capacitor. This energy can be retrieved since an ideal capacitor cannot dissipate energy. In fact, the word capacitor is derived from these elements, capacity to store energy in an electric field. And we should note the following important properties of a capacitor. Note from I is equal to C dV over dt that when the voltage across a capacitor is not charging with the time, like for example, DC voltage, the current through the capacitor is 0. Thus, a capacitor is an open circuit to DC. However, if a battery or DC voltage is connected across a capacitor, the capacitor is charged. Next is the voltage on the capacitor must be continuous. The voltage in a capacitor cannot change abruptly. The ideal capacitor does not dissipate energy. It takes power from the circuit when storing energy in its field and returns previously stored energy when delivering power to the circuit. A real non-ideal capacitor has a parallel model leakage resistance as shown in figure 6.8. The leakage resistance may be as high as 100 ohms and can be neglected for most practical application. For this reason, we will assume ideal capacity. Next is we're going to solve practice solving on the capacitor. So this is one of the example of the capacitor, and what is the voltage across a 5 microfarad capacitor if the charge on one plate is 0.12 microcoulomb? How much energy is stored? So ang atong gipangita ka is pila ka buok voltage ang og how much energy ang na-stored. So, given is our capacitor is 5 microfarad, and then ato ang charge Q is ang 0.12, and ato rin pangitaan ng voltage. So, ang atong gamitan na formula is ganina is ang Q is equal to CV. So, since gipangita man ang voltage, atong i-manipulate ang formula into this. V is equal to Q over C. So, this one, we are going to use the formula. So, ato siyang i-plot ang mga value. So, V is equal to, ang Q is 0.12. Turn natin siya into column. 0.12 times 10 to the negative. Since it is a micro column, it is negative 3, while 5 times 10 to the negative 6. Since it is a microfarad. So, V is equal to Q 0.12 times 10 to the negative 3 all over our capacitor is 5 times 10 to the negative 6. So, we're going to calculate it. 0.12 times 10 to the negative 3 divided by 5 times 10 to the power of negative 6. So we get V is equal to 24. So now, we are going to find how much energy stored. So, as you can remember, the formula nga ato ang gamiton is this one. Is equal to 1/2 CV squared. So, atong i-plot into 1/2. The capacitor is 5 times 10 to the negative 6 times the voltage is 24 squared. So, 1/2 5 times 10 to the negative 24 squared is 576 times 576. So we're going to calculate it. 1 times 5 times 10 to the negative 6 is equal to divided by 2 times 576. So the answer is 100.44 times 10 to the negative 3, or 1.44 times 10 to the negative, sorry, is equal to 1.44 millijoule. And this is the energy stored. Now, another example of a problem of the capacitor. So, the current through a 100 microfarad is, the current is 50 sine 120 pi t milliampere. Calculate the voltage across it at t is equal to 1 millisecond, t is equal to 5 millisecond, and a VO is equal to 0. So, to calculate this, we need to use a current voltage relationship of a capacitor, which is, the formula is I is equal to C dV over dt. But we are asked about the voltage. We are asked about the voltage, so we need to manipulate this formula, and we will manipulate it into V is equal to 1 over C, which is the capacitor, and then integral of I dt. So we will use this formula and we will plot the values. So V is equal to 1 over, since the capacitor is 100 microfarad. So 100, since it is a microfarad, times 10 to the negative 6. And then integral of our IT is 50 sine 120 pi t dt. Since it is a milliampere, we will put the value of 10 to the negative 3 into here. So we will put it times 10 to the negative 3. And first we're gonna divide it. So V is equal to, we should calculate it into 1 times 10. And we will get the value of 10. And then integral of 50 sine 120 pi t dt, and we're going to multiply this. So V is equal to 500 integral of sine 120 pi t dt. So we will integrate this and then Vt is equal to integral of sine is negative cosine. So the sign will be negative, so 500 and then over 120 pi, and then cosine 120 pi t plus C1. Since we are integrating, we will have this, and then we need to find the value of C1. So our VO is equal to 0. So negative 500 divided by 120 pi, and cos sub 0 plus C1 is equal to 0. Since cos times 0 is 1. So the value of C1 is equal to 500 over 120 pi. Yes. So we will put into our original form, into our Vt is equal to negative 500 over 120 pi cos 120 pi t plus 500 over 120 pi. And now we will going to solve the time, the 1 millisecond and 5 millisecond. So remember our VT is equal to negative 500 over 120 pi cos 120 pi t plus 500 over 120 pi. And we will, to solve the 1 millisecond, we will just plot the time here. So V times 10 to
to negative 3 is equal to 500 over 120 pi cos pi, and then the time is times 10 to the negative 3 plus plus 500 over 120 pi, and we will get the answer of 0.09314 volt, and we will convert it into millivolts, so we could get 93.14 millivolts. This is for 1 ms. So to solve the other one, same process, 5 ms, so V 5 times 10 to the negative 3 is equal to negative 500 all over 120 pi cos pi, cosine, it is cos 120 pi, and then the time is 5 times 10 to the negative 3 to the negative 3 plus 500 all over 120 pi. Sorry, this is 120 pi. But we could still find the answer this one. Pi, and we will calculate it into here. We could get the value of S is equal to 1.736 volts. So
Now we are going to talk about the series and parallel capacitors. Series and parallel capacitor, we know from resistive circuits that the series parallel combination is a powerful tool for reducing circuits. This technique can be extended to series parallel connection of capacitor, which are sometimes encountered. We decide to replace this capacitor by a single equivalent capacitor, or C equivalent. Note that the capacitor have the same voltage across them. So as you can see here in the figure, where A figure and B figure is, this one is, the A is a parallel connected end-to-end capacitors, and this B is equivalent circuit for the parallel capacitor, where C equivalent is equal to C1 plus C2 plus C3 plus ... plus Cn. The equivalent capacitance of n parallel connected capacitor is the sum of the individual capacitance. The figure A is a series connected n capacitor, and B is the equivalent circuit of the series capacitor, where 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus ... 1 over Cn. The equivalent capacitance of the series connected capacitor is the reciprocal of the sum of the reciprocals of the individual capacitance. Note that the capacitor in series combine in the same manner as the resistor in parallel. For example, two capacitors in series. And we could get this formula: C equivalent is equal to C1 C2 over C1 plus C2. And examples of the series and parallel connection.
So now this is another example of a capacitance, and here the problem is find the equivalent capacitance seen at the terminals of the circuit. And this one, it is a series and parallel of the capacitance. So if we have parallel capacitor, so the equivalent capacitance will be here is equal to C1 plus C2 blah 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 Cn. And if it in series, we will use this equivalent series is 1 all over 1 divided by C1 plus 1 divided by C2 plus dot 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 C1 over Cn. So as you can see in the circuit, this one is parallel, so we will solve this one. So since it is parallel, we will use this one. So 50 microfarad plus 70 microfarad is equal to 120 microfarad. So now this capacitance is already 120 microfarad. Now, as you can see in the circuit, this 60 and 120 is in series, so we will solve this one into series. So we will use this one. So 1 over 60 plus 1 over 20 is equal to 1 over 2 over 20, 120, sorry, this is 120, plus 1 over 120, or 1 over 1 over 120 is equal to 120 over 3. Oh, sorry, this is 3. So we could get 40 microfarad. So this one is already a 40 microfarad. Now the 20 and the 40 is now already in a parallel, so we will add this into 20 plus 40 microfarad is equal now to 60 microfarad. Now the circuit will be look like this. This one is already, the circuit is 120, so we put it here, 120 microfarad. And then this circuit is already, we solve it all, it's already 60. So 60 microfarad. So see equivalent. Now we will solve this. Oh, say, let me go back since wala nakita sa video. The circuit will be look like this since kani siya atuan na ning giad, since it is a parallel. So na 120 ni siya. So mo na ni ang circuit. Karon atuan naman ning gi total tanan pod, which is first gi series nato ning duha. Mo na nakuha nato ang 40. Pagkakuha sa 40 ato di siya gi parallel, so which is kani. So 60 microfarad. Now ang circuit may mo na siya ingon ani, and then since it is 120 and 60 are in series, so we will solve it. C equivalent is equal to 1 over 120 plus 1 over 60 plus 1 over 1 divide 120 plus 2 divided by 120 is equal to 1 over 3 over 120, and then 120 divided by 3, we will get the C equivalent. We could get 40 microfarad, and this is the final answer.
So now we are going to talk about inductors. An inductor is a passive element designed to store energy in its magnetic field. Inductors find numerous applications in electronic and power systems. They are used in power supplies, transformers, radios, TVs, radar, and electric motors. An inductor uses a conductor that it wound into a coil. And when electricity flows into the coil from the left to the right, this will generate a magnetic field in the clockwise direction. You can see it in the figure below. The voltage-current relationship for an inductor is directly proportional to the time rate of change of the current through V is equal to L di over dt. The voltage across the inductor is zero unless the current is changing. Thus, an inductor acts like a short circuit to a DC source. The current through an inductor is directly proportional to the time integral of the voltage across it. And this is the formula that we're going to use. And the current through an inductor cannot change instantly. Inductor in series and parallel are combined in the same way resistors in series and parallel are combined. So as you can see in the figure A and B, A is a series connection of N inductors, while B figure is equivalent circuit for the series inductors. Where this is a series connection of N inductors, where L equivalent is equal to L1 plus L2 plus L3 plus ... plus Ln. This is the parallel connection of N inductors. As you can see in the figure A, it is a parallel connection of N inductors, and figure B is the equivalent circuit of the parallel inductors, where 1 over L equivalent is equal to 1 L1 plus 1 L2 plus 1 over L3, plus ... plus 1 over L. Inductor, at any given time t, the energy stored in a capacitor is 1/2 CV squared, while the energy stored in an inductor is 1/2 Li squared. And we should take note of this in the inductor, where the capacitor is 1/2 CV squared and the inductor is 1/2 Li squared. Examples of the inductor practice problem.
This is one of the practice problem of an inductor. So if the current through 1 millihenry inductor is IT is equal to 60 cosine 100t milliampere. Find the terminal voltage and the energy. So in this problem, we're gonna find the voltage and the energy stored. So in the voltage, we will be using the formula of Vt is equal to L di over dt di over dt and for the energy stored, we will be using the formula of W is equal to 1/2 inductor and then the current squared. So first, we're going to solve the voltage. So Vt is equal to the inductor. We could use we could rewrite it into a scientific, SI unit. We could rewrite it into SI unit, which is 10 to the negative 3 Henry. So our inductor is 10 to the negative 3 times d over dt and our current or IT. And now we will calculate it into 10 to the negative 3 times d over dt, and our IT is 60 cosine 100t milliampere, or we will plot it here into 60 cos 100t, and then we will bring down the 10 to the negative 3, derive it into this one. Here the derivative of cos is negative sine 100t, and then this one 6,000 negative 6,000t, and we will multiply this. We could get Vt. We could get negative 6 sine 100t, and this is our voltage or Vt. Now let's proceed to calculate the energy stored, and we will be using this formula. So W is equal to 1/2 Li squared. So is equal to 1/2 times 10 to the negative 3, the value of our inductor, and then our I is 60 cos 100t milliampere. So times 60 cos 100t, since the value of it is milliampere, we will times it into 10 to the negative 3 before we squared it. So we will get 1/2 times 10 to the negative 3, and 60 squared is 3,600 times 3,600 cos squared 100t, and then this one is times 10 to the negative 6, and then we will proceed here 1/2 times 10 to the negative, we will multiply it 10 to the negative 3 times 10 to the negative 6, we will get 10 to the negative 9 times 3,600 times 3,600 and 3,600 cos squared 100t. We could just cancel this out and we will get 1,800. So our here is 1,800 times 10 to the negative 9 cos squared 100t joule. And we could convert it into microjoule. So we could get our work is equal to 1.8 cos squared 100t microjoule. And this is our answer of our energy stored. So this is one of the example of a inductor, and the problem is given to calculate the equivalent inductance. So let's start. We will calculate this one into series, this one. So 40 plus 20 is equal to 60 millihenry. So this one is already 60. So we will, the 60 and the 30 is in parallel. So we will calculate it into 30 times 60 divided by 30 plus 60 is equal to 30 times 60 all over 90. And this one is cancelled. We will make it into 3 and we will get 20 millihenry. So this one is 20 millihenry. So the circuit will be look like this. 20 millihenry. 20 millihenry. This one is 100 millihenry. 40 millihenry and 20 millihenry and then 50 millihenry. So we get this 20 millihenry into the parallel of 60 and 30. And now we will calculate this 120 into series. So 100 plus 20 is equal to 120. So 120 millihenry is in parallel to 40. So we will solve it into 40 times 120 divided by 40 plus 120 is equal to 40 times 120 all over 160. So we'll cancel out, it will be 4 and we could get 30 millihenry. So this equation is already 30, I mean this circuit here, part here is already 30 millihenry. So we will rewrite here, this circuit will be look like this. This will be 30 millihenry. This is 20 millihenry. This one is 50 millihenry. And then 20 and 30 is in series. So we will just add this both. So 20 plus 30 is equal to 50 millihenry. So the equation will be look like this. They will be in a parallel. So this one is 50 millihenry and 50 millihenry. So we will calculate this into 50 times 50 divided by 50 plus 50 is equal to 50 times 50 divided by 100. So cancel 2 and then we could get 25 millihenry. So the circuit will be look like this. The equivalent inductance is 25 millihenry. This is the final answer.